Okay, so next question is, when is a Riemann sum an under-approximation and when is it an over-approximation? Well, that really depends on what you're looking at. So far, we've really only talked about a left Riemann sum and a right Riemann sum. So let's say we've got a couple different things here. So let's look at these two shapes. So here we're concave down, here we're concave up. Now, if we have endpoints, so I'll put in some dots here, let me put them in black so we can see them a little bit better. So we got some endpoints, right? So for our first shape, when we look at a left Riemann sum, so between these two, I'm using the height on the left side. So between these two, I'm using the height on the left side. So the question is this an over-approximation or an under-approximation? Well, right now, I'm under, because you see all of this area that I'm missing here? So it's an under-approximation. However, as we get to the right, when I start using the left over the right, look what happens. So here's the left, here's the right way down here. So now all of a sudden I'm using a left-hand Riemann sum. I'm doing an over-approximation because left's up here and right's down here. So when are we an over-approximation and when we're in under? So it's not the concavity because this is concave down the entire time. So again, this is for left. Let's look over here. We have some endpoints. So for a left Riemann sum, we have an over-approximation right now. So we have these two endpoints. I'm using the one on the left to make my rectangle. These two, I'm using the one on the left. Because my area of the curve is here, but I got a bunch of extra area over. Now on this side, my left is here, my right is here, so I'm way under approximating this area. I'm leaving out all of this area here, and all this area here. So it's be under. So a left is an under-approximation. So let's see here, when we're increasing. Or f prime of x is greater than 0. So a lot of times that's what we're looking at. And you can explain it as either that it's increasing or f prime is greater than 0. So the right is under when, so the right Riemann sum would be exactly the opposite. So if we're talking about a right Riemann sum, when is the right going to be under the left? Well, the right's going to be under the left when we're decreasing, right? The right hand side is lower than the left hand side. That's what it means to be decreasing. So and then the converses are also true. So left is under when we're increasing. It's over when we're decreasing. So over when decreasing. And the right is an over when increasing. But I would really draw it out and be like, okay, so we have an increasing function. So the left side is going to be lower than the right side if we're increasing, because the right sides are higher than the left. That's what it means to increase. Now, there's two more types. Now, the two types that we still have to talk about are midpoint and trapezoid. So trapezoid basically looks like this. You got a left and you have a right. Now, here, it'll be a little easier to talk about it this way. So these two here, if I draw a trapezoid in there, I get a better, a closer approximation than either a left or a right. However, right now, we're under approximation because we're missing some of the area here. We don't get all this area in the middle. If I connect these two dots here and make a trapezoid, we're still a lot better. However, we are missing a bunch of area in the curve. So the trapezoid is an under approximation when we're concave down, and it's over when concave down, concaved up. Okay, so this video we're going to just spend a little more time with the Riemann sums and talk about the midpoint and the trapezoidal sum. So I'm going to skip over part A. It's almost exactly the same thing as part A for the last problem and the last video. And we'll go right to doing just more Riemann sums. So the first thing, we want to use correct units to explain the meaning of this in terms of rocket flight. Okay, so to go from velocity, the antiderivative velocity is position. So you have basically your position of 70 minus your position at 10. That's what this exactly gives us. So what is it? It's our displacement or our change in position. Over the time period. Now, again, always make sure you do this in terms of the rocket's flight. So it should say something more along the lines of this is the displacement of the rocket during the time between 10 seconds and 70 seconds. Okay, so that's the meaning of this. So what we want to do is use a midpoint Riemann sum with 3 subintervals. Okay, so we want to make sure we start at 10 and end at 70, so keep track of that. So we're not doing this entire thing, we're only going from 10 to 70. Now midpoint, now it says 3. So if we're doing a left Riemann sum, we would start with 14 and go to 22, and then we go from 22 to 29, and we would use the height of 14 and the width of 10, height of 22 and the width of 30. Except we've got way too many of these going on here. And how do you do a midpoint? Because if I'm going from 10 to 20, I got 15 somewhere in the middle, but I don't know the height. So what we have to do for midpoint is we're going in bigger chunks. So we're looking here. So between 10 and 30, the midpoint is 20. And it's actually a much easier problem than the other ones. So what's my height of my midpoint is 22 times my width of not 10 to 20 or 20 to 30, but from 10 to 30. So my width of 20 plus, and then I go to the next one, my midpoint is here. So 35 is the height, and my width is 20 as well. And the last one would be here. So the middle point between these two is a height of 44 and a width of 20. Then you have to work this all out. Now, let's say, just so that we can talk about how to do it, what if it didn't say a midpoint? What if it said use a trapezoid? Okay, so instead of midpoint, we're going to trapezoid. So here's the deal with the trapezoid. Area of a trapezoid, and we'll stick from 10 to 70, we'll write down some of them, is, you probably see it this way. Ooh, that's a terrible trapezoid. Come on. Alright, it's hard to draw on this thing. So you probably see it this way. Base 1, base 2, and we have a height. And the area is 1/2 base 1 plus base 2, the average of the bases, times the height. Or, you might have seen it with the 2 on the bottom. It doesn't really matter. So it's basically the average of the bases times the height. So here's the difference. For these, we're talking about left endpoint, we have a right endpoint. This is the x-axis, and we have 2 different ones. So the thing you have to realize is this is a trapezoid kind of tilted sideways from what you're used to. So this will be our base 1, this will be our base 2, and this is our height down here. It's always perpendicular, which is kind of nice. This side won't be perpendicular, but the x-axis will be. So, which ones are my bases? These are the bases. So in this case, we're going from 14 to 22. I'm not using 14 like I would for a left endpoint. I'm not using 22 like I would for a right endpoint. For the trapezoid, I got to use the average of the two. I'm going to do 14 plus 22 divided by 2 times the height of 10. And then you just go to the next chunk. So which one do I use, the left or the right? No, I don't. This is not the midpoint. Don't get me wrong, the midpoint would be at 15. I'm not going to be necessarily at 15. I'm using the average of the heights. So it seems like a midpoint, but it's not really. So I do 22 plus 29 divided by 2. So the average of my bases times my height of another 10. The book talks about taking these 10s out, or there were 20s here a minute ago. But these x's do not have to be 10 apart each time. They can be apart by like 5, 10, 7, 3. It doesn't really matter. And you go from one to the other one. So the next one would be 29 plus 35. Divide this by 2. Just the averages times the height of 10. And you do the next one, 35 plus 40 divided by 2 times the height of 10. 40 plus 44 times divided by 2 times the height of 10. 44 plus 47 divided by 2 times the height of 10. You go until you're going from 10 to 70. And that is how you do a trapezoidal Riemann sum.